Electrons tend to be described as tiny particles that move freely within materials, transporting electrical current and responding to external fields. However, under very concrete conditions, that everyday behavior breaks down and gives way to collective phenomena that are difficult to observe and even more to understand. One of them is the so-called Wigner crystal, an exotic phase in which electrons cease to behave like a DAS and spontaneously order themselves to form a regular structure. If you are interested in the world of quantum physics and electrons, we invite you to subscribe to our channel and give like to this video. Each subscription helps us to continue creating interesting and educational content for you. A group of researchers have now been able to directly observe this type of electronic crystal with unprecedented resolution, using a new type of two-dimensional quantum material. This finding not only confirms decades of theoretical predictions, but opens up an unprecedented experimental pathway to study collective states of matter dominated by interaction between electrons and not by their individual movement. A Wigner crystal is a state of matter in which electrons are organized into an orderly network. This phenomenon appears when the electrical repulsion between electrons exceeds their kinetic energy, forcing them to stay separate and adopt relative fixed positions. In that regime, electrons stop flowing and behave like a solid. The main problem with studying these crystals is their extreme fragility. Any external disturbance can destroy the electronic order. For that reason, although Wigner's crystal was theoretically proposed almost a century ago, its direct observation has been exceptional and always limited to indirect signals. In addition, most traditional electronic microscopy techniques alter the system they try to measure. In the case of Wigner crystals, that interference is sufficient to erase the sought-after structure. Hence the importance of developing methods capable of seeing without disturbing, a key condition that this new work has managed to fulfill. The studied system consists of a single atomic layer of ytterbium chloride, placed on a graphite substrate. This combination is not arbitrary. When both materials come into contact, there is a spontaneous transfer of electrons from the graphite to the monolayer, concentrating them on extremely flat electronic bands. One of the most relevant aspects of the work is the use of Q+ atomic force microscopy, a technique that minimizes electrostatic disturbances. Thanks to this approach, the researchers managed to visualize directly the Wigner glass network, something that did not appear in the images obtained with conventional microscopia. The electrons observed in this system are not only ordered, but have an unusual property, an enormous effective mass, hundreds of times higher than that of a free electron. This characteristic reinforces the mastery of electron-electron interactions over individual movement. The developed system offers an alternative to other flat band materials. This allows to study in more detail the competition between kinetic energy and electronic correlation, one of the central problems of solid-state physics. The discovery leaves open multiple lines of research. One of the most intriguing is the study of the layer of holes left in the graphite, coupled to the electronic glass. This combined system could lead to new collective states, such as exciton crystals or other hybrid phases not yet described.